Hello children, welcome to my chemistry class. I am Javashri Ghosh, teacher in Demonstration Multipurpose School, Bhubaneswar. Children, I am really happy to have you all with me. Although we have not seen each other, but I feel so connected with you all and I am trying my best to help you all with your chapters. Children, in last class, we had started the third chapter of your science book, that is atoms and molecules. And even we have covered some portion of that. Today, we'll learn some more new concepts. Before that, children, let me tell you, get ready with your NCERT books, your notebooks and pen. Are you ready, children? Shall we start? Today, the topics to be discussed are atoms, size of atoms, symbol of atoms and elements, atomic mass. These are the topics we'll be discussing. But children, before that, let us just brush up our memory. That is, recapitulate the concepts we have done before. In our previous classes, we had done laws of chemical combination. What were the laws? We had done two laws, laws of conservation of mass and law of constant proportion or law of definite proportion. What do they say? Law of conservation of mass. Mass can neither be created nor be destroyed in a chemical reaction. What about the law of constant proportion? The elements are always present in definite proportion by mass in a chemical substance. For example, we had considered that of water. In water, hydrogen and oxygen are in the ratio 1:8 by mass. I hope you remember all these things, children. Next, we had also done the postulates of atomic theory by John Dalton. What were the postulates? They were, the matter is made up of tiny particles called atoms that cannot be divided. Atoms are never created or destroyed during a chemical reaction. Atoms of an element exhibit same nature. They have the same size, mass and character. Atoms of different elements exhibit variant nature. They do not have same characteristics. Children, we had discussed, I had shown you some figures like elements A, element B having different type of atoms. I hope you remember all these things. Next is, atoms form compounds by combining in a ratio of whole numbers. As I had told you, it is always H2O or H2O2, CO2. We never find H2.5 with O 3.6. Do we ever? No. Next is, a compound contains a constant number and kinds of atoms. Okay, children, this is about brushing up our memory. Now, today, just look at this. What is going on over here? Can you say? Okay, here a wall is being built up. Okay, how do we build up a house? First, we pile some bricks. We make a wall or the number of walls needed. Then we connect it. Is not it? That is how a house is built. And the houses are given different shapes. But remember one thing. Like, what is the starting material for that? We start with the bricks. Very initial step is the bricks. Bricks are the fundamental units. Okay. Similarly, children, for matter, atoms are the fundamental units. Atom combine to form matter. Atoms of same element, they form a molecule. Atoms of two or more different elements, they form compounds. We will learn about that in the later part of this chapter. So, let's know what are atoms. Children, just imagine I have a piece of paper. If I go on cutting, I will come to a point with certain bit that shows the character of paper. That becomes the atom of paper. Okay, if we cannot do it mechanically, we can do it by some other way. But the last part is the atom. As we had discussed, you might feel atoms have got some subatomic particles like electrons, protons, neutrons. We'll learn in the later chapters. But children, those things do not possess the property of atom. Like atom of oxygen. Suppose you have element oxygen. Atoms of oxygen has the property of oxygen only, but the subatomic particles, electrons, protons, neutrons, they do not exhibit the property of oxygen. So, the building block of the element is always an atom. So, children, what is an atom? What are the different characteristics of atom? The atom is the basic building block of chemistry. I'm saying chemistry. Why chemistry? Because basic building block of chemistry is elements and compounds and molecules and all those things. And basic building block for that is the atom. Okay. An atom is the smallest unit of matter that has the characteristic properties of a chemical element. Thus, as I have told you, the last bit of paper will show the characteristic of paper only. The last bit of one atom of oxygen will show the characteristic of oxygen. Okay. An atom is the smallest unit which takes part in the chemical reaction. Actually, whenever a chemical reaction is going on, atoms are the smallest unit which take part. Okay. An atom is a particle of matter that uniquely defines a chemical element. Their characteristics, their properties, their physical properties, their chemical properties, their behavior, everything is governed by the unit particle, that is the atom. An atom is the smallest unit into which matter can be divided without the release of electrically charged particles. We are saying electrically charged particles means we are talking about the subatomic particles. Okay. Now, let us come to the size of atom. What is the size of atom? It goes beyond your imagination, the size of atom. The size of atom are very, very, very small. The size of atoms are measured in nanometers. What is that nanometer? We denote it by nm. 1 nm, as you see on the screen, children, it's written 1 nm is equal to 10 to the power minus 9 meters. Can you imagine how small it is? Let me give you an example. Suppose, children, everybody, you have a scale with you. Is not it? You have a scale. In the scale, you have the marks of centimeter as well as the millimeter. The smallest division you see over here is 1 millimeter. This much. When, children, you will divide that 1 millimeter into 10 lakh parts. Just imagine 10 lakh parts, 1 with 6 zeros. The small part, that is nearly the size of the atom. Can you imagine? It's not possible to see with our naked eyes. That can be shown by high electron microscopes. Okay, high power microscopes. Children, so you have an idea how small is the size of the atom. Let us give certain comparisons so that you have a broader idea. Here I have got some atoms of hydrogen with the radius in meters. Here you have written radius in meters. About atoms of hydrogen, molecule of water, molecule of hemoglobin, grain of sand, ant and watermelon. We start with the atom of hydrogen. Atom of hydrogen is 10 to the power minus 10 meters, that is 0.1 nanometer. That very small. And on comparison, we last come to the watermelon, which is the radius is 10 centimeter, that you can see with your naked eyes. Even a grain of sand, one grain of sand is difficult to see with our naked eyes. Children, so you can go to that limit of imagining how small an atom can be. Now children, let us talk about the symbols of atom. We just can't write oxygen, hydrogen, sulfur, chlorine. We cannot just write those things. We have to denote it by certain symbols, because if I'm writing, I talk about the carbon dioxide, okay? Carbon dioxide, I have to write the full 3 words, carbon dioxide. In many reactions, when carbon dioxide reacts with so and so, we get so and so. It becomes a very long sentence. It's wasted of time and energy. So it's very necessary to write them in symbols. And that too, one more importance is that if you are writing or using the symbols, from those symbols also we can know what is the proportion of the elements in a compound and how many atoms are used up to make that compound. So, symbols of atoms. Dalton was the first scientist. Dalton, he has lots of contribution in chemistry, children. Dalton was the first scientist to use symbols to represent elements in a short way. Dalton's symbol for an element represented the element as well as one atom of that element. Let's see. Dalton's symbols of atoms. Now children, you are seeing on the screen certain symbols and the names of the elements also. Dalton's symbols included circles. You can see those circles over here containing distinct symbols. A dot for hydrogen. Inside the circles, you have dots and some other notations also. See here, a dot for hydrogen. Inside the circle, a cross for sulfur. All of you look at the screen and here. If you want, you can note it down also. Children, you have these symbols in your NCERT books also. Don't worry. You can just listen to me and see look at the screen. C for copper, L for lead. You see lead inside the circle, L is there. For copper, inside the circle you have C. For potash, you have some lines. For alumina, you have some dots, 4 dots. Phosphorus, 3 lines. Oxygen, the plain circle. Sulfur, a plus sign is there. Okay. So, these were the initial symbols. Don't compare with the symbols we are using it now. We'll move to that. But Dalton's symbols were this sort. Okay, then it was improvised. Now, what about the compounds? Dalton's symbols of compounds. How? Like water. You know children, water, hydrogen and oxygen, they form water. See the symbols hydrogen and oxygen. Do you feel that it's quite easy to use the symbols and write the symbols? Okay, water is okay, ammonia is okay, olefin gas. Olefin gas is carbon and oxygen. Okay, then carbonic acid. Carbonic oxide. See, sulfur acid. For sulfur, they have used this oxygen and the sulfur. Potash alum, such a big symbol. When you are writing these symbols, if you use these symbols in a chemical reaction, what will happen? You are going to make big drawings and diagrams. Is it easy for you to remember? No, definitely not. It becomes difficult for us to remember. So, this needed It was improvised. They needed some changes. Now, how the changes were done? Now the things we are following were the changed ones. Modern symbols of atoms. What are the modern symbols? Chemical symbols are abbreviations used in chemistry for chemical elements, functional groups, and chemical compounds. Element symbols for chemical elements normally consist of one or two letters. That we are using it now from the Latin alphabet and are written with the first letter in the capital. I will show you the examples, the symbols we are using nowadays. Okay, how these symbols were used. See here, children. You have certain elements, certain symbols and origin of their name on the screen. See here, children, hydrogen. Hydrogen is got from the Greek word hydro and gen, and that is denoted by H. Similarly, C for carbon. In Latin, it means coal. N for nitrogen, it's a Greek word. O for oxygen, it's also a Greek word. Gen is the forming. Okay. Hydro is water forming hydrogen. F, fluorine. Fluorine means in Latin to flow. P, phosphorus. It's a Greek word, means light bearing. It gives out light. Light bearing word. S is sulfur. In English, it is sulfur, and in Latin, it is sulfur. I denotes iodine. That is the violet color. In Greek, I've told you, generally our modern symbols are got or proposed by the Greek or the Latin words. Okay, children? But children, these elements, those I have shown, and some other elements are also there. These are generally used elements. They have the symbols with just one English letter, that is in uppercase, that is the capital letter. Okay. But I'm sure you might have come across certain other symbols with a capital letter and a small letter. Is not it? Yes, we'll see how they are formed. See here, children. We have certain symbols, elements and origin of their name. Here we have used one capital letter and one small letter. Why did we go for that? Why? Helium, that is from the Greek word helios, means sun. He. We denote helium by He. Why do we do this by He? Because if you are using the starting letter, we had used it for hydrogen. So there will be some confusion. To avoid those confusions, we are using first two letters of certain words to denote those elements. Helium, He. Neon. It's a Greek word, neo. From that neon, Ne. Why Ne? For nitrogen we had used N. Magnesium. That is from the word magnesia. That is Mg. Okay. We have with M lots of elements. Magnesium, manganese, molybdenum. All these words. So, to avoid those confusion, we are using the first two letters, Mg. Then comes aluminium. The Latin word is alumen. Let me tell you one thing, children. If you want, you can note it down. You have your notebooks and pens with you. Okay. So, if you want, it will help you in your long run. And even some of you are interested in general knowledge also, you can have this for your general knowledge. If not for your exam purpose, you can use it for your general knowledge or some other important exams you will be appearing. You may need this. So, children, it's better if you make a note of it. Then comes chlorine. Chlorine, Greek word greenish yellow. That is, we denote it by Cl. Argon. In Greek, idol. Why do we call it idle? Because they're least active elements. These are noble gases or inert gases. Okay. So, argon, Ar. Calcium, it's a Latin word for lime. Okay. That is Ca. Greek, in Greek, color is chromium, Cr. Cobalt, Co. All this C, and along with that Cc, we are using the second alphabet in the lower case, that is in the smaller letter. Okay. Cobalt, it's a German word, we use Co. Copper, it's an English word from the Latin word cuprum. So you use Cu. And zinc, and it's a German word zinke, prong or the tooth. It's named for the tooth, and it is Zn. Okay, children, you have a very rough idea why we use two letters to make it a symbol for certain elements. Okay, children, let's go for this is one more special case. Till now, we have used the first two letters of those name of those elements. But here, you see, these are quite different. What is the difference, children? For sodium, we are writing Na. Sodium. Sodium is something you feel like So or Sd, something should be there. But is it the fact? We are having sodium as Na. Why this happens? This, we have directly taken it from their original name. The original name for sodium is natrium. Remember this, take it down, it's very important. Children, write it on your notebooks. Sodium, it is from Na, the symbol is Na from the word natrium. Potassium, we denote it by K, and it's from the Latin word kalium. Iron, we denote it by Fe, and it's from the Latin word ferrum. Silver, we denote it by Ag, and it's from the Latin word argentum. And tin, the Latin word is tannum, and we denote it by Sn. What about gold? Gold, the Latin word is aurum, and we denote it by Ag. Mercury, in Greek word is hydrogyrus, and we denote it by Hg. What about lead? The original Latin word is plumbum. So you use Pb. Okay, Pb for lead. Children, please make a note of it. I am telling it repeatedly. You may have questions from these also, and you'll be using these symbols throughout your, till you study chemistry. You should not forget this. You have to remember these words. Okay, children? Now, let's come to the checkpoint. What is the checkpoint? Checkpoint, like just brushing your memory. What we have studied, you just see the questions on the screen and you write the answers, then I'll discuss. What are the symbols for the following elements? For sodium, copper, mercury, calcium. I'm waiting, children. Hope you have written it down. Okay. It needs just few seconds to write it down. Did you write Na for sodium? Put a tick mark over there. If you have written Cu for copper, put a tick mark and cheer yourself. What about mercury? Is it Me? No, sorry, it's Hg, mercury. If you have written Hg, big tick. And that last one is calcium. Calcium is Ca. Those who have done, you have got 4 out of 4. Next question is, why is it necessary to use symbols for elements? I have discussed with you, children. Do you remember? I have told you why it is necessary to use the symbols for element. Remember that big notations. Are we supposed to write, if we write ammonium chloride, I'll make the symbol for ammonia, then I'll write ammonia, then I'll write hydrogen, then I'll write chlorine. Is it possible to do it always? No. So why it is necessary to use symbols? To make it, shorten it. And from the symbols, we can also know the elements which are forming the compounds, or what is the proportion of the atoms that are taking part in the reaction or forming the compounds. So it is very necessary to use the symbols for the elements. Okay, children, take note of it and write in your notebooks. So, what's the last question? What are the Latin names for the following elements? Children, I told you to take it down. You might have noted it. Tin. Latin name? You know it, stannum. What about lead? It is plumbum. What about gold? It is aurum. Silver, argentum. Potassium, calcium. So, little bit brushing is done. Now you brush up your memory and just try to recollect those name of symbols for the elements we'll be using. These children, you have to remember it. If you practice 2 or 3 times, you will remember it. Also read your NCERT books. That's very important to go through your books and use these things and make note for yourself. Okay, children? Now, let's go for how to determine the mass of atom. Size of atom you have known. I told you it's very, 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 so very small. And I showed you how small it can be. Now you have an extent of imagination how small an atom can be. Now, mass of atom, that too. It is also very, very small. Since atoms are very, very small, is it possible, do you feel we can weigh those atoms? No, children, it's not at all possible. We cannot weigh the atoms. Okay, we cannot find the absolute mass of atoms as we weigh our potatoes, we weigh our grocery, we weigh gold and silver in kg and all. But mass of atom, can you imagine? No, it's not possible to find the absolute weight. If it is not possible to find the absolute weight, but we need it for our experiments and demonstrations, so what should we do? It was the scientist, and especially Dalton, they found a way out. They found the mass of atoms. They found the relative mass of atom comparing with other atoms or elements. Let's see how this is done. Mass of atoms, since the size of atom is very small, hence directly measuring its mass is not possible. The concept of atomic mass was first proposed in Dalton's atomic theory. According to Dalton, each element has a characteristic atomic mass. Okay? This theory was able to explain the law of constant proportion. We know that. Thus, scientists use the law of chemical composition to calculate the relative atomic mass of the elements. How it is calculated? See here, concept of atomic mass. In earlier 19th century, the chemist adopted the hydrogen atom as a standard of mass and set its atomic weight at 1. Children, as I have told you, since it is difficult to find the absolute mass of an atom, so it was necessary for them to find the relative mass by comparing with other atoms. First, they thought that they would compare it with hydrogen. Okay. But they could find that standard mass of hydrogen was set at 1. But that's not true, and that didn't work out because hydrogen has some more like isotopes. The word isotope might be new for you. You will learn in the later chapters. But let me tell you, the hydrogen equal to the mass of hydrogen had got certain parts, not parts actually, certain other type of elements which has same mass of hydrogen, like hydrogen, tritium, deuterium, all these things. It was similar to hydrogen. And when everything was taken into consideration and when they started comparing the atoms with the mass of hydrogen, the masses of atoms started coming in decimals. Okay. So, when something is in decimal, huge calculations became very tedious. And they found that hydrogen was not suitable. The atomic mass of hydrogen now we assume as 1, but actually it is 1.003. So, hydrogen, they were not very comfortable. Scientists were not very comfortable with hydrogen. Then what's the next step? The next step was they thought of some element which is reactive. It reacts, it is found in abundance, and it has a tendency to mix with other elements also, and that came out to be oxygen. Okay. They even tried, say, in 1850s, what happened? Chemists used a unit of atomic weight based on saying the atomic weight of oxygen was 16. Through different experiments, okay, by law of definite proportion and by experimenting with different compounds of oxygen, they assumed that weight of oxygen was 16. Oxygen was chosen because it forms chemical compounds and many other elements, simplifying determination of the atomic weights. One atomic mass was taken as 1/16th of mass of oxygen. It was taken as the standard unit. But this also didn't work out. And the same problem happened, like atomic masses of many elements came in decimals, and all those calculations and all became very tedious. So this was also not considered. Finally, which was considered and till we are following it, that is in 1961, nearly after 90 years, and universally accepted atomic mass unit, that is carbon-12. Isotope was chosen as standard for measuring atomic mass. Why the word carbon-12 is there and isotope is there? I told you carbon-12, another isotope of carbon is there, that is carbon-14. Okay. So, here the word isotope is used. Carbon-12 suited this purpose perfectly. Carbon-12 was the perfect element to be chosen for making a standard for measuring the atomic masses. Okay. One atomic mass unit. Now, one atomic mass unit was taken to be 1/12th of the mass of carbon-12 atom. Okay, children? See, 1/12th of C12 was taken to be the standard for measuring the atomic mass unit. And atomic mass of carbon was considered to be 12 AMU. What is that AMU? AMU means atomic mass unit. So, children, how do we define atomic mass? Atomic mass of an element may be defined as the average relative mass of an atom of the element as compared with the mass of an atom of carbon, that is C12 isotope, taken as 12 AMU, that is atomic mass unit. Okay, children? So, here, see here, example calculation of atomic mass. 3 grams of carbon combined with 4 grams of oxygen to form 7 grams of carbon monoxide. This shows that 4/3 carbon reacts with 4/3 mass of oxygen of it to form carbon monoxide. 4/3 means how can you find the atomic mass of oxygen? Just you can look at the screen. 4/3 into 12 is 16 AMU. So, atomic mass of oxygen was considered as 16 AMU. As per the recommendations of IUPAC, AMU is now written as U, that is the unified mass. What is IUPAC? International Union for Pure and Applied Chemistry. They approved the things. So, AMU has been approved to be written as U, that is the unified mass. Here we have the atomic masses of some elements over here. Children, have a note in your mind that you must remember first 20 elements, atomic masses of first 20 elements, because you need in your calculations. Later on, we'll come with those calculations and you need them. These also you can find in your books. Then comes the final part of this, that is the assignment. Children, what all we have discussed, you can use those to write the answers for these questions. Please note it down, children. Define atomic mass unit. You know it. Why is it impossible? Why is it not possible to see an atom with the naked eye? We have discussed. Third question. 6 grams of carbon-12 reacts with 71 grams of chlorine to form carbon tetrachloride, that is CCl4. Find the atomic mass of chlorine. The one we had done in the example. Question number 4. We know the atomic mass of oxygen is 16U. Determine the relative atomic mass of nitrogen. If 7 grams of nitrogen reacts with 16 grams of oxygen to form nitrogen dioxide, NO2. Please note down these questions, children. So, let us stop here. We are at the end of today's class. Children, bye for today. Take care, stay home and stay safe and be fit. Okay, bye.